In this video, we look at Thevenin Theorem for circuits with dependent sources involved. Let's look at RTH. How do we obtain RTH? If the network has dependent source, first of all, we turn off all independent sources but leave the dependent source on. In other words, the dependent source, we do not do anything for them. Then we add external voltage source or external current source. So if we add external voltage source, we want to add a V0 here. Normally we choose V0 equals to 1 volt for simplicity. Then we calculate I0. RTH equals V0 divided by I0. If V0 equals to 1, so that equals 1 over I0. We can also add external current source I0, and then we calculate V0. Pay attention to the sign of V0. When we're adding the voltage source, pay attention to the direction of I0. It has to define this way, okay, to flow into the network. If we add a current source I0 here, normally we choose I0 equals to 1A, just for simplicity. Then RTH equals to V0 divided by I0, because I0 equals to 1, that equals to V0. So there are two ways to obtain the RTH for circuits with dependent source involved. First of all, we turned off independent sources. Then we add external sources, either a voltage source or a current source. Pay attention to the current directions and the sign of the voltage. This is how do we obtain the RTH. How do we obtain the VTH? To find VTH, we open the terminal and obtain the open circuit voltage. Now is the time to do a summary to obtain the VTH and RTH for Thevenin Theorem. First of all, VTH. Regardless if the network has dependent sources or not, it is obtained by the open circuit voltage. So we just open the terminal, calculate the open circuit voltage. For the RTH, regardless if the network has dependent sources or not, it can be obtained by the ratio of VTH and the short circuit current. So VTH, that's open circuit voltage, and ISC, that's the current of short circuit at the terminal. Note in this case, if we choose to calculate RTH in this way, the independent sources are not turned off when we calculate the short circuit current. There are other ways to calculate RTH. If the network has no dependent sources, then we turn off the dependent sources. Then the circuit only contains resistors. RTH can be obtained by using parallel or series simplifications. If the network has dependent sources, then we turn off the independent sources. That's first step. And then we add an external voltage source or an external current source, and then we proceed as described in the slide 45, which is this step. Either we add a voltage source or we add a current source, and then we take the ratio. Next, let's look at this circuit. How do we obtain the VTH and RTH for the Thevenin equivalent circuit? In this circuit, we have controlled source, which is a voltage controlled voltage source. Question asks us to obtain the RTH and VTH in the terminal of A and B. To find RTH, first of all, we turned off all the independent sources. There is a current source. We turn it off. How do we turn it off? We want the current flow through this branch goes to 0, then we open circuit. So therefore, this current source being turned off. So the circuit become this circuit now. So the variable Vx still here, that's the voltage along this 4 ohm resistor. This is a controlled source. We didn't do anything about it. It's still 2Vx. And we add external voltage source, which is 1 volt. and we define I naught this direction, and RTH equals V naught divided by I naught, because V naught equals to 1, this is equals to 1 over I naught. So the question is to find I naught. To find I naught, there are many ways here. You can use mesh, you can also use nodal, whichever way is convenient. So in this case, we illustrate using the mesh analysis. We have mesh I1, mesh I2, and mesh I3. And by the way, I naught equals to minus I3, because I3 flow into this direction, I naught flow into this direction here. They are in opposite direction. So if we solve all of this mesh current, I1, I2, I3, we can obtain I naught. And then once we obtain I naught, we take the ratio that equals to RTH. Let's look at mesh I1. So when we walk here, the first element is minus 2Vx, because this is a voltage source, and then come back here, that will be 2 ohm. The current flows through 2 ohm will be I1 minus I2. So, and then get rid of 2 here, get rid of 2 here. This equation is simplified at this now. Vx equals I1 minus I2. Then let's look at Vx, because this is a controlled source. So Vx, that's extra variable. We need to get rid of it using the mesh current. Vx equals to minus 4I2, because I2 goes to this direction, but Vx, the sign is marked this way. So therefore Vx equals to minus 4I2. Plug in Vx to here, and then we can obtain I1 equals minus this relationship. The variables is I1 and I2. So one equation here. We need two other equations to solve I1, I2, and I3, 3 unknowns. We need totally 3 equations. So let's look at mesh I2. We walk here, that will be 4 I2, right? And then plus 2 I2 minus I1, that's the voltage, and then 6 I2 minus I3, I2 minus I3, that's current flow through this 6 ohm resistor, that equals 0. That's one equation. Let's look at mesh 3. Mesh 3, we start from here, that will be 6 multiplied by I3 minus I2, and then 2 here, 2 I3, then plus 1. This is the voltage here, that equals 0. Now we can solve this 3 equation using MATLAB, using matrix. Once we obtain I3, we obtain I naught. I naught equals 1/6 M. So therefore RTH equals to 6 ohm. To obtain VTH, we open the terminal. This is the open terminal voltage, VOC. As we said, that VOC, that's open circuit voltage, it doesn't matter what the notation is, that equals to VTH. So we need to solve this circuit to obtain VTH. And notice that there is no current because it's open circuit here, open terminal here. There's no current flow through this 2 ohm resistor. So therefore, VTH or VOC, that's the voltage along here. So this is here, VTH. We need to solve this circuit to obtain VTH. And again, we can use mesh analysis. Notice that this independent source is here now. To obtain VTH, we do not do anything for the independent source. We do not turn them off. Mesh I1, is that equals to 5A. There's one equation already solved. Let's look at mesh 2 here. 4 ohm, I2 minus I1, and this 2 ohm, I2 minus I3, and then here 6 I2. So that's mesh 2. Let's look at mesh 3. mesh 3, minus 2Vx, and then 2 ohm, I3 minus I2. Come back, that equals 0, and then Vx equals to I3 minus I2. Get rid of this 2, get rid of this 2. But what is Vx? Remember, this is a sign here. This is a plus sign. This is a negative sign. Vx equals 4 multiplied by I1 minus I2, because I1 goes to this direction. If I take the difference of I1 minus I2, then the combined direction is going to flow down. That will agree with the passive sign convention of Vx. Therefore, there's no negative sign here. There's a plus sign here, no negative sign in front of 4 here. So that's Vx. Plug in Vx inside here. 3 equations, 1, 2, and 3 equations. And Vx, that's a function of I1 and I2. We plug it in, and then we obtain I2. If we solve I2, then VTH equals to 6 I2. As I said, VTH, that's the voltage along this 6 ohm here, that equals to 20. This is a Thevenin theorem, Thevenin equivalent circuit. VTH equals 20 volts, and RTH equals to 6 ohm for this circuit.